All right, everybody. Thanks for joining me. It looks like I see a lot of familiar faces on the participants list on Zoom. A lot of old friends, a lot of coworkers. So thanks a lot for kind of joining our presentation, or joining my presentation. For those of you that don't know me, my name is Josip Injić. I also go by Josip Injić or Josip, or not Josip, but Josip. I'm an iOS developer at Capital One. And I'm also the organizer of DCiOS, as well as a co-organizer of this conference. DCiOS is a meetup that we host every month, usually in DC, but we've been virtual ever since the pandemic. Always love having you people come join us in there or even volunteering to speak. If you want to find out more about DCiOS, come and check out DevCommunity.org, and you'll actually see a link to DCiOS as well as our other meetups that we have there as well. Today, we're talking about the fifth sense, the power of vision. And really what I mean by that is VisionKit, the VisionKit framework. What is vision and what can it do for us? Well, it does a lot of things. For example, like in sports, it can handle tracking objects and analysis of the human pose. With accessibility, it can handle things such as OCR and object detection, helping visually impaired users. Within health, it can do things such as like barcode scanning and the human pose. Within computation photography, vision helps us handle things such as portrait mode because it relies on face detection and segmentation. For security, we can use things such as face recognition and motion detection. The analysis of documents, and face and body related requests, which is another one of the topics we'll dive in a little bit more today. As you can see, the vision framework covers a lot. So let's get started with the document detection. Vision offers a number of requests that help you with analysis of documents. They include barcode detection, text recognition, commonly known as OCR, contour detection, rectangle detection, and new for this year, document segmentation detection. Today, we'll quickly cover barcode detection. Most of our time, we'll be going over text recognition and document detection within this specific segment. There was a new revision that was given to us at WWDC. VN Detect Barcode Request Vision 2. It gave us support for more new symbologies, and they include CodaBar, DataBar, DataBar Expanded, DataBar Limited, PDF 417, and MicroQR. You can use these in a varieties of like maybe in stores when you're going through shopping, or even just stamps when you're sending them out. These are all scannable. In revision 1, the binding box gets reported in relation to the full document. So here you can see the document being the white space, that's the highlighted space taking up the entire document there. And that's kind of how revision 1 worked. Revision 2 actually allows us to specify an ROI or a region of interest. So for example, it could be like the middle part of our camera. And we'll have some examples that we can go over to kind of show that off. It can detect multiple codes and symbologies at the same time within that region of interest. So here's a great example. Using the iPhone, multiple codes can be scanned at once, and because it's connected to the internet, you can pull up the information right away without needing another device. You can see in this app that the area of interest is defined in order to scan these barcodes. You also see this like when you're scanning your credit card for Apple Pay or something like that. There's always like an area of interest where you can scan the information. With iPhone's low light capabilities, you can even scan codes in low light scenarios, just as in this example, without disturbing the patient. Let's move on to text recognition. Text recognition was introduced in 2019. It operates in 2 modes, fast and accurate paths. The fast path goes through a character-based recognizer as opposed to an accurate path's ML-based recognizer. For those of you who aren't familiar with the term ML, it's just a machine learning or machine learning-based recognizer. Both paths go through language correction and output the recognized text. And the great thing is, all this happens on device. So the first two portions of that, both for the fast and accurate paths, are go through or are dependent on, I guess, a language and the script. So what's great about this all being done on the device? Well, it allows the data to process a lot quicker since there are no network calls happening. And more importantly, information remains confidential, such as in the example of them using in the hospital. Never leaves the device. Everything is done there, is computed there, and we never have to worry about any sniffing tools or anything like that picking up calls being sent through an API. Let's take a look at this document, and we'll zoom in to get a better idea of how the different paths work. So the fast path breaks each character apart. It passes it through language correction and returns us the result. The accurate approach detects words and sentences and then passes it through a deep learning model to determine the words on the document. It's much more like humans actually read text. This is then passed through language correction and returns the result. And I'll say that for the accurate path, it's a lot better at interpreting text with crazy fonts or different types of like styling, whereas a fast path is a little bit better for normal fonts, I guess. And we'll see some examples of that. One for the fast path would be something similar to this, where you see the sign happening or written in a different language. So here we can use the fast path to take the text, digitalize it onto the device itself. And then while we have that code there, right, we're translating that text now into English and then rendering on that screen. And we need to use the fast path because we want to quickly be able to render this live for a user while they're looking on their device. A great use case for like the accurate path might be reading information from like a check during a mobile deposit, for example. Here we can validate that the value in the courtesy line and the legal lines match. For those that aren't familiar with those lines, the courtesy line is where you actually write in the amount for the check, and the legal line is, or sorry, actually the other way. The legal line is where you actually write it in, like actual text. The courtesy line is where you would like write in the number in the little box. And here in this case, we can see that these numbers don't match. And we can verify that because we can convert a string into an integer when we're using Vision. The accurate path is best used when we can handle the text in post-progressing, meaning we don't need it right away for the user and we can take our time to determine it correctly. A situation like this, it's super helpful because now we can, if we have a bank app, for example, we can mark this check as potentially fraudulent because these two lines don't match up. And maybe you have a form in your app where the user has to input a bunch of information. What if they can import that information directly from a document? We can go through and select the text and values that are most critical to our form and pass that with the image through the API to help speed up the process for the user by avoiding having to type in any of this info. Think of this scenario. It's an app where you scan in your receipts, something all small businesses do for tax purposes. Now later you find, later you need to find a receipt for like a specific purpose. Well, if we scan receipts with the accurate path, we could search through all the receipts that the users ever scanned in order to find the specific one they're looking for. So in this case, I can search for something such as Main Street Restaurant, and it should provide me the actual receipt that I'm looking for, and it'll actually highlight the text that I want. You don't have to like download any fancy app to do this. Your Notes app will actually now do this with the latest installation of iOS 15. Here's another example we all might be used to. Using the camera, we can scan text of our credit cards to make a purchase. Or if you ever added a credit card to your Apple Wallet, it does the exact same thing. We're using Vision to specify our region of interest and doing a fast path over the card to scan. It'll also, if you ever use the Apple Card or adding a card to Apple Card or Apple Pay, it'll like show digital text on the screen, basically allowing you to like verify that it matches with everything that's on the card. Now in iOS 15, we can even scan text in our camera app. There's a picture behind me that you can't see, but it's this picture that I have Cleveland. So I kind of took a picture of it in the frame. And you can see here, it's already like setting little highlighters around the text. Even though this is a script, it's like a little bit difficult to read, but it's using the accurate path on here to like better determine this text. And I can actually highlight the text in this image, which will give me some actions to perform in the text. From here, I can copy it, look it up, translate it, or share that text. In my case, I look up the text Cleveland, which did a great job reading, even in this fancy script. You can see in the definition where it states it's the best city ever with an amazing football team, go Browns, and tropical weather. Let's move on to the next part of vision. So we'll talk about the human pose a little bit. Why would you want to add this to your app? Maybe your app can help a coach show how his players are incorrectly moving their arms to shoot a basketball. On a professional level, it can be analyzed and played back to a viewing audience at an NBA game using 3D imaging and the body analysis to replicate the shot. Similar things can be done with soccer or football, depending on what country you're coming from. Instead of using the data coming from the arms, we can focus on the lower body data points and landmarks to provide a similar result that we'd have with the previous example. I said we can determine the positions of our hands as well. We could build an app that lets you track your fingers when you're playing the guitar, for example. It could be used to help a young guitar player like show that she's making mistakes when she's playing the guitar. With these examples, let's take a look at how we can actually build out these apps. Using vision, we can detect landmarks in the hand. Each of the circles on this image is a landmark. Vision can detect a total of 21 landmarks for each hand, 4 for each finger, 4 for the thumb, and 1 for the wrist. Each of these fingers is in a joint group, depicted by the API via human hand pose observation and an enum called joints group name. As you can see, obviously, we get 5 of those in the enum: thumb, index, middle, ring, and little finger. In each joint group, every individual joint has a name. And for the fingers, they're dip or tip, dip, mip, or pip and mip. The distal interphalangeal joint, and there's a few other ones in there. They're tough to read. So that's why I didn't go into the healthcare field. The thumb's a bit different. It has a tip, but the other joints have different names. You know, I think a lot of developers think that they don't need math in their careers. Who would have thought anatomy would have been a prerequisite for this too? Using vision, we can also detect landmarks. Using vision, we detect landmarks in the hand. Now with the ability to detect these top points, we can match them with the strings on the card to detect mistakes when you're playing it. Let's get creative here by like introducing the core ML framework so that we can interpret hand poses and actions. So we use core ML to integrate machine learning models into our apps. Core ML provides a unified representation for all models. Your app uses core ML APIs and user data to make predictions and to train or fine-tune models. And this all happens on the user's device. Basically, you're passing some model which is interpreted by core ML on your app. On the left side, we have hand poses, which are meaningful as still images. Even though these images are paused, the intent of the subject is clearly expressed. One guy is piecing out, and another lady is telling you to stop. Whether it's in a video or in a still image, it makes sense, hence it's a pose. On the other hand, we have actions. If we pause these GIFs at any one frame, the intent wouldn't be obvious to us. But in a video or live photo, it's clear that the actions are come here or waving hello because it requires a movement to express it. And this year, we have 2 new Create ML templates. They're hand action classifications and hand pose classifications. We'll take this data as a model. We can train it and then integrate it into our app. So here I'm trying to create a simple app where I can put up one finger and it'll give me the hand emoji that correlates with that, with the one, a peace sign for the 2-finger hand emoji, and 5 fingers up for the 5-hand emoji. In order to do that, I have to create a model that holds all these poses. So you can see here I have 2 folders, one depicting a bunch of people holding up the 1 finger, and another one depicting people holding up the peace sign. But you notice there's also a background folder. So background consists of any pose that doesn't relate to the ones you're looking for. Think of it as the junk folder. Not only should it consist of wrong poses, it should also contain transitional poses. Think about putting up the peace sign. You have to transition your hand to lift those fingers up. The poses during that transition need to also be added there. So if you're thinking of frame by frame, right? We only care for the pose once it's as full peace sign, not as a transition. Same with the 5 fingers up. There's a transition there that we need to include into that background category. The rest will categorize in their own folders, again at its full form. Now we'll simply add this data to the core ML app and train it. That model can then be integrated into an app so that when we do lift up 1 finger, the app can reply back with the 1-finger emoji or the 2-finger emoji or the 5-finger emoji, depending on how many fingers we're holding up. Now this other app, we can see presenting certain poses can show off power beams. These 2 apps use the same core ML model. But here we can see, for example, that when she does have the 1 finger up in a live video, we can see a power beam coming from her finger, 2 fingers showing 2 power beams or putting it together. But it's exactly the same core ML model, and using vision to detect those fingertips and kind of display the beams from there. Another thing that was added this year is chirality. And this allows us to identify the left versus the right hand. Using vision, we can determine one at a time which hand is the left and which hand is the right. Now, just because one hand is a right hand doesn't mean that the other hand is a left hand. It'll determine it individually. You could have 2 right hands in a screen, so it does a really good job of picking out each one individually. Hand actions will capture a sequence of hand poses. Remember, this one should have to take a video or live photo in order to determine the action, right? Because again, if we pause it at any point in the frame, if the action doesn't make sense, then we can't really do much with it. Just as before, we need to provide models of these actions, but you'll notice this time it's being done with actual video files. And same thing here, we need to define in our background all the different kind of junk ones that we don't want to include in our actions, right? If we're looking for a hand rotation, then a wave is not the same thing, and we need to add that type of video in to the background side. One big difference is that the trained data should include an annotation file in either a CSV or JSON format. And they typically include labels such as the actual label, video start and end times for these individual videos. Here we can see both hand actions and poses being used. We're able to track the rotation of the hand as an action and the left hand having its finger up. We can perform similar actions to using landmarks in the body in general. And I love this video. I feel like this is going to be a Zoom background for me at some point. Well, let's take a look at some of the landmarks that we can detect when looking at the body as a whole. So here are 2 of my favorite Croatian soccer players. And if we look at some of the landmarks that they have, we can see what they can detect here. You can use Vision's capabilities for detecting human body poses on its own or with Core ML. Combining Vision with the power of machine learning enables a wide variety of feature possibilities. For example, a safety training app could help employees use correct ergonomics. A fitness app could automatically track the exercise as the user performs it. And a media editing app could find photos or videos based on the similarity of the poses. We can detect these landmarks using VN human body pose observations. They also come with their own joint name. And you can see them listed there. Now, there are a few things that we need to keep in mind to accurately detect the human pose. The subject's height should ideally be at least a third of the overall height. A large portion of the subject's key body regions and points should be present in the image itself. So here, if you remember from the old I'm a Mac and I'm a PC commercials, this is kind of the ideal shot that we want when we're determining any body region or anything like that, or the body landmarks. It's kind of a full shot. They take, there's good lighting, easy to capture this using vision. Probably a bad example is something like this, right? There's no body shot in here. It's taking up the entire picture. It doesn't work. A subject wearing flowing or robe-like clothing reduces the detection accuracy too. Same thing can be said if you're like trying to use the hand poses or hand actions. Wearing something thick like gloves could also distort or lower the detection accuracy. Detecting body positions in a crowd could also be difficult, as you can imagine with this one. Vision can have a hard time depicting like where it needs to pick off from in this here image. Now, we barely scratch the surface of hand and body detection APIs in Vision, but the possibilities with it are endless. Now, in this, we covered barcode scanning, analyzing documents and text, hand and body landmarks for Vision, as well as the amazing use cases when merging it with CoreML. And that's pretty much all I wanted to cover today for Vision itself. A lot of these use cases that we talked about could be used, like I said, in the health field with accessibility to determine if like object is in front of you, like let's say for a blind person. It can be used in sports. We use this with our portrait mode to determine depth and like the face for taking pictures, security, document analysis, and just in general, the human pose. But that's pretty much all I have to cover today. And I want to see if there's any questions I can take from people. Tibbetts doesn't believe that there's tropical weather in Cleveland. There is Tibbetts.
No, there's not.
I had a question.
Yeah, go ahead.
So, like, I play soccer, so I'm just curious about this. If I wanted to train, like object detection for like a soccer player who's like passing or making a cross or shooting, I would just like put in like 1,000 images of a player shooting and say, like, feed it to the CoreML machine, and then on Xcode, and then another 1,000 images for passing, another 1,000 images for like crossing and making a headshot or something like that.
Yeah, so it wouldn't be pictures in that case because you're performing actions. So I'd say you would pass in actual videos. So just similar to how we were like looking at the different hand actions, you're looking at the same thing as like body actions. So you'd be passing in videos of that. But yeah, just like you said, you'd go through and add in different ones for each of those type of categories, as well as like your background file of like everything that is not any of the ones that you're looking for. And yeah, using Vision, it already really easily detects the landmarks on the body as you're taking in a live feed frame by frame. So you're like it's able to kind of bring that all out for you. And the better your model, the better the result that you're going to get out of it. And then I think Sebastian had a question in regards to what I'm using. I'm using for the presentation, I was just using Keynote, so free on your Mac. But Muhammad, did that answer your question for you?
Yes, thank you.
Yep. And there's a lot of cool new features on iOS 15 if you guys haven't got a chance to play with it. Even on like your camera app, for example, or sorry, your texting, like if you want to do a texting, you can actually go and like grab texts like live within the texting app, and it'll copy directly over to like the text field while you're texting. So I like to play with it. Like if I'm watching Netflix or some show and you have captions open, you can actually just like watch have it like just play live on the TV as it's going, and Vision will like automatically just pop in each line of captioning into your text, which is super nifty, and it's extremely accurate and fast. It stays like very quickly up to date with everything that's popping up on the screen. You want to have any other questions?
I just had one other question. And let's say like there's an actual image on my phone right now, like the app can detect it now successfully, like if I'm shooting or passing, like that just takes like a split second. Are there any kind of like identifications that take a huge amount of time? Which ones are those? If so?
You mean like action identifications, or you're just like thinking landmarks in general?
Any sort of like identification. I'm just thinking about like what kind of identifications. I don't know if of the ones that you just showed us today, are any of them like taking more than the average that it takes? Like I don't know what the average is, by the way.
Oh, to compute, yeah. I mean, so I'd say more than the average. No, I think it all comes down to, again, to your model. Like I think they all compute. I think the action ones take a little bit more to compute than the actual image ones. So whenever you're like for example, in your example, I think you were talking about like a kicking goal versus passing in soccer. So those type of like, you might have to have more processing that occurs there, but it's still fairly quick in relations to, I guess, I don't know, just in general. It's definitely very quick when you have it on there. I played around with a little bit. I haven't used that example particularly. My experience has been more with the hands itself and the different actions and poses I can kind of take on there. And I have seen that the actual hand actions, they do take a little bit longer for it to compute, but we're talking about like less than a second. And I think the other thing there is that the detection accuracy for me ends up being a little bit lower than what it would be with the actual poses, since those are like still images. And because it is like, you can have like weird detections, it actually does give you like it gives you feedback in like how accurate it thinks it is. So you can actually write in your code like, hey, this is less than like X% accuracy, like don't even include it as part of like the feedback that you're giving me in the app.
Gotcha, thank you.
Mm-hmm. Well, if no one else has any questions, guys can always reach out to me on Slack. I'm also on Twitter. I think I posted a hashtag on the slide there a few times. So hopefully you caught that. If not, yeah, Slack is the place to go.